Good morning, students. Today we are going for the second unit, network transients. The prerequisites of network transients is your fundamental mathematics. So first order differential equations, second order differential equations in terms of time domain. So in that you are studied how to find the complementary function and also particular integrals. Then Laplace transform. So in terms of S domain analysis, you have to do. And the one more prerequisite of this unit is basic electrical engineering. There you studied the passive active elements when they are connected in series and parallel. Okay. So coming to the subtopics of your unit 2 and unit 4 is almost similar, because unit 2 based on the first order system, second order system using time domain analysis, and your fourth order we are going for the S domain analysis. So almost similar. So that's why the total subtopics related with unit 2 and unit 4 are. So coming to the transient behavior of the system only. So in that, so you have to go for the initial values of your passive elements. So resistance, inductor and capacitor. At the same time, final values of your passive elements. So that discussion you have to do. And the transient behavior of RC, RL and RLC series circuits. So for DC excitation and the AC excitation, then what is the time constant for a RC circuit and a RL circuit? Then you have to go for the S domain analysis. So using Laplace transform. So what is a initial theorem? What is a final value theorem? And conventional integral. And also you have to go for resonance in AC circuits. So in resonance also, it is divided into two categories. One is a series resonance. So R, L, C are connected in series. We are studying the resonance behavior of a electrical circuit in connection with the series connection. And similarly for parallel connection, there are three cases are there. So in that three cases, how when a resonance is occurred, so what is the impedance we are calculating and what is the admittance we are calculating. Then the last topic is network functions. So any electrical network can be represented in terms of impedance transformation or transfer impedances. So with respect to their limitations and the necessary conditions, we are going for the transfer function. So transfer function is the ratio of output to input. So in that you can get a polynomials S domain values in the numerator and also in the denominator. So if you substitute the numerator value is equal to 0, then you can get the zeros of the equations. Those roots are zeros, and if you substitute the transfer function as infinity, you can get the poles in the equation. So while you are plotting the zeros and poles in a S domain, so you can go for the stability. So stability of the system also we are studying at the same time. So what is a magnitude plot and what is a phase plot also we are studying in this unit. Okay. So now come to the transients. So what is a transient? So the best example you can go for the transient is a electrical tube light. So if you switch on the tube light, so it will take certain time. So after few seconds, so it will be get into the steady state. So before that, it behaves as a transient response. So that's why once the switch on the tube light, so it will be blinking. It will be blinking for a certain few seconds. After completion of the transient period, then it comes to the steady state motion. So in that you don't have any disturbance in the glowing of a light. So why you are getting like this means it is a series connection of resistance, inductance and capacitance. So once a supply is given, the initial values are changes. So the current flowing through the circuit will be changes. The voltage drop across the each element, resistor, inductor, capacitor will be changes. According to that, there is a transient behavior will occur. So due to that, the blinking will be there. Once it passed out, then you can get a steady state analysis. Under that condition, there is no changes in the resistor, inductor and capacitor. So that change you are calling as a transient response. So the transient response will completes. After that only you can get a steady state response. So that's why the transient response can be named as a natural response, and the steady state response can be named as a forced response. So for a particular system, if you are giving a switching supply, so automatically there must be two responses. One is a natural response and another one is a forced response. Natural response you can call it as a transient response, and forced response you can call it as a steady state response. So to go for the solution for this particular network, so you have to go for time domain analysis, or you can go for the classical method, Laplace transform. There are so many transformation techniques are there. Fourier transformation technique is there, jet transformation technique is there, but in your syllabus is limited to Laplace transform only. Okay, so the behavior of natural response and forced response must be getting in time domain analysis with respect to complementary function, as a transient behavior, and particular integral must be a steady state behavior. Okay, so while you are coming to the Laplace transform, there is no problem. Directly you can get the solution of the equation. That is the advantage as compared with the time domain analysis of a Laplace transform. Okay, so now one by one parameter initial conditions we are choosing. So first I am taking a pure resistor. So a pure resistor R ohms is excited by a V of t. So a current will flow through circuit when the switch t is equal to 0. So that means the switch will be closed at t is equal to 0. So then a current of I of t amperes will flow through the resistor. Okay. So according to Ohm's law, so the current can be represented as I is equal to V by R, or voltage drop across the resistor can be represented as V is equal to R into I. Okay. So here for you are going for the transient behavior of the circuit. So the t is equal to 0 must be taken with two instants. So one is t is equal to 0 minus condition just before the switch is closed position. Just before the switch is closed position, which indicates still the circuit is open circuit only. The circuit is open circuit only. Then at t is equal to 0 minus condition. So immediately the switch is closed. Immediately the switch is closed. So the circuit is having a closed path. The circuit is having a closed path. Okay. So let us assume there is no initial values of the resistor. So at t is equal to 0 minus, so still the circuit is not closed just before the circuit is closing position. So under that condition, the I of 0 must be 0. I of 0 minus must be 0. Then at t is equal to 0 plus condition, at t is equal to 0 plus condition, just immediately the switch is closed, a current will flow through the closed path, so through the resistor. Then by Ohm's law, I of 0 plus must be V by R. So this is your time domain analysis. While you are going for the Laplace transform, So V of S is equal to R times of I of S. So here the resistor never depends upon any time value. So there must be no initial conditions for the resistor. So that's why the resistor initial value and final value must be same. Anyway, we will discuss in the final values also. Okay, so under that condition, I of S is equal to V of S divided by R. So that is the current flowing through the resistor R ohms. Okay, so then coming to the inductor. So inductor never takes instantaneous currents. Inductor never takes instantaneous currents. So let us assume a pure inductor L Henry is connected to a voltage source of V of t, So at t is equal to 0, the switch will be closed and I of t will flow through the circuit. So at t is equal to 0, we are having two conditions. One is t is equal to 0 minus condition, and another one is t is equal to 0 plus condition. So 0 minus means just before the switch is closed position. 0 plus means immediately the switch is closed position. So let us assume the inductor is relaxed position. So that means no initial currents in the inductor. So under that condition, at t is equal to 0 minus condition. So what is the current? There is no closing of the switch. No current will flow to the circuit. So it is open circuited. So I of 0 minus is also 0. I of 0 minus is also 0. Then at t is equal to 0 plus condition. At t is equal to 0 plus condition, the inductor never takes the instantaneous currents. So after closing the switch, just immediately the current I of t will flow to the inductor, and the inductor never takes the instantaneous currents. So it is not taking the instantaneous currents means what? No current will flow to the circuit. So under that condition also you can get I of 0 plus is 0 amperes only. So this is the equivalent circuit. At closing of the switch at t is equal to 0. So the inductor will act like a open circuit. The inductor will act like a open circuit. So in this condition, we have taken no initial conditions in the inductor. Now, whenever there is a initial current is there, let us assume the initial current is I of 0. There is an initial current is there. So under that condition, the I of t value can be represented as 1 by L integral 0 to t V of t plus I of 0 plus you have to consider. So I of 0 plus means this is the initial current. It is equivalent to I of 0 only. It is equivalent to I of 0 only. So the inductor never takes the instantaneous currents. It is act as an open circuit. So due to the previous source, the initial current is there. So it acts as a current source. So this is the equivalent circuit represented for the initial condition of an inductor. So inductor is open circuited, but due to the initial current, the current source must be present with the same direction of your inductor current. With the inductor current. Okay. So this is time domain analysis. So while you are coming to the Laplace transform also, so V of S is equal to L into S, I of S minus L into I of 0 plus. So I of 0 plus is what? I naught only, initial current only. So similarly, we want to write in terms of current. So I of S is equal to V of S by L into S plus I of 0 plus divided by S. So these are the equivalent circuits represented in terms of Laplace transform. Both are same. So this is the figure represented for time domain analysis, and this is the figure represented for Laplace transform. Are you understanding? So coming to the capacitor, so let us take C is farads of a capacitance of a capacitor. A voltage V of t is applied across the capacitor. A current will flow through the circuit at t is equal to 0. So at t is equal to 0, you can get the two instants. One is t is equal to 0 minus condition. Another one is t is equal to 0 plus conditions. So let us assume this capacitor has no initial charge. This capacitor has no initial charge. So that means it is under relaxed position. So no initial voltage across the capacitor is there. So according to the voltage equation across the capacitor is 1 by C integral IDT, or if you want to write in terms of current, so I is equal to C dV by dt. So now at t is equal to 0 minus, no, at t is equal to 0 minus, so just before the switch is closed position, still no current will flow through the circuit, so the current flowing through the capacitor must be 0. Then at t is equal to 0 plus, just immediately the switch is closed, the applied voltage will be across the capacitor. So capacitor never takes the instantaneous current, instantaneous voltages. Capacitor never takes the instantaneous voltages. So that means the capacitor will act as a 0. Will act as a 0. So that is voltage drop across the capacitor is 0. So it is short circuited. So at t is equal to 0 plus condition. So the capacitor will act as a short circuit, and the current flowing through the circuit must be considered as I of 0 plus condition is the value of current flowing through the circuit. Okay. So then coming to the initial charge or initial voltage across the capacitor. So let us assume due to previous source there is a initial voltage across the capacitor V0. So is applied at t is equal to 0 with a voltage of V of t. A current of I of t will flow through the circuit. So V of t is equal to, the basic equation is 1 by C integral 0 to t I of t plus V of 0 plus. So here V of 0 plus is V naught only. So V naught is the initial voltage across the capacitor. So the capacitor never takes the instantaneous voltages. It acts like a short circuit, and whatever the voltage across the capacitor can be replaced by a voltage source. Can be replaced by a voltage source with the same sign. So plus to minus only. So if it is minus to plus, you have to represent the voltage source by minus to plus. If it is a plus to minus, you have to represent the voltage source by plus to minus. So this is the equivalent circuit in time domain analysis. So similarly, if you want to go for the Laplace transform, so the current flowing through the capacitor I of s is equal to C into S into V of s minus C into V of 0 plus. So in terms of voltage means V of s is equal to I of s by C into S plus V of 0 plus divided by S. And this is the equivalent S domain analysis of the circuit. So both are same, time domain or Laplace transform, you can get the same only. Okay. Then coming to the final values of the passive elements. So final values means at t is equal to infinity condition. So resistor never depends upon the time. So because by Ohm's law, V of t is equal to R into I of t, you are writing. So that means the resistor never depends upon the time. So that's why at t is equal to 0 or at t is equal to infinity, there is no effect of resistance and there is no initial charges or initial currents flowing in the resistor. So it is purely depends upon the resistive material of the resistor only. Then coming to the inductor, so the voltage drop across the inductor is L di by dt. The voltage drop across the inductor is L di by dt. So that means this inductor will depends upon the time. Will depends upon the time. So if you substitute t is equal to infinity, di by d infinity you can get. So that means di by dt or di by d infinity will become as a 0. Then the inductor acts like a short circuit. The voltage drop of inductor is 0 means it acts like a short circuit. So inductor at final value, so we are getting a short circuit condition. Initial value you can get a open circuit condition. Okay, then coming to the capacitor, so the capacitor current can be represented as I is equal to C dVc by dt. So where Vc is the voltage drop across the capacitor. So whenever at t is equal to infinity condition, dVc by dt, so that is dVc by d infinity, so you can get 0. So that means the current is 0. So current is equal to C times of 0. So that is 0 only. So current is 0 means the capacitor will act like a open circuit. So at t is equal to infinity, this capacitor will act like a open circuit. Are you understanding, students? So this is the initial and final values of the passive elements. Then coming to the summary, so once again I am recalling. So inductor never takes instantaneous currents. So it must be remember. So it never takes the instantaneous currents. So that's why only the inductor will be open path under initial state. So capacitor never takes the instantaneous voltages. So it never takes the instantaneous voltages means the voltage drop across the capacitor is 0. So initially it acts like a short circuit. So at t is equal to 0 plus the inductor is open circuited. At t is equal to 0 plus the capacitor is short circuited. So which is related to your first and second points only. So whenever any initial current is there, at t is equal to 0 plus, the inductor will be open circuited and the current source must be represented in parallel with the open circuit inductor. So and polarity must be same whatever they are given in the circuit. So at the same time, at t is equal to 0 plus, any initial charge in the capacitor or voltage drop across the capacitor is there. So we have to replace the short circuited capacitor in series with the voltage source, and the polarity must be same as given in the circuit. So that is your next point. And at t is equal to 0 plus and at t is equal to infinity, the resistor remains changed without any changes. It must be remains unchanged without any changes. Okay. Then coming to the t is equal to infinity condition, the inductor will be short circuited and the capacitor will be open circuited. So these are the conditions with respect to DC voltages. If it is a AC voltage, it will be permitted. It will be permitted. Are you understanding? Then coming to the Laplace transform. So the conventional method is time domain analysis. So in the time domain analysis, for a simple first order systems, also you have to go for the complementary function and particular integral. So to find the constants of these, so again you have to go for the initial values. Initial values. By applying the initial values, you have to go for the calculation of the constants. So while you are coming to the classical method called Laplace transform, so the entire it may be a first order system or it may be a second order system. So the representation of equation will be very simple, and once you are going for the partial fractions, the residues you have to calculate with a very simple way. So once you calculated the residues, then the overall transfer function by taking the inverse Laplace transform, you can get the time domain analysis. You can get the time domain analysis. So basic equation you are writing, then you are converting into Laplace transform. By using partially differential equations, you are calculating the residues. After that, again you are going for the inverse Laplace transform for getting the time domain equation of your solution. So it is a very simple process for finding. It may be a first order, second order, or nth order systems. So that's why this Laplace transform we are calling as a classical method. Classical method. Okay. So generally the Laplace transform function can be represented as Laplace transform of f of t is equal to f of s, that is equal to integral 0 to infinity f of t e power minus st dt. Are you understanding? So if you want to go for the inverse Laplace transform, so inverse of f of s is equal to f of t you can get. Are you understanding? So that is the inverse Laplace transform. Then coming to some important test signals which are used in the Laplace transform techniques or in the time domain analysis techniques for transient behaviors. For transient behaviors. So the major three different test signals are unit step response, delta function or impulse function, and ramp function. So these are the three different test signals. So step response is similar to your square response only. So there is no big change. So in the square response, you have to go for particular time limit to reach zero. To reach zero. Okay. So here you are going for the different types of step responses. You are going for the different types of step responses. So it is a unit step. So that means the maximum value of your step is 1. The maximum value of your step is 1. Then you can say that it is a unit step. So unit step means at t is equal to certain, at t is equal to 0, you can get one value, and it must be constant forever. It must be constant forever. Then you can say that it is a step response. So the u of t can be represented as 0 less than or equal to 0. So because less than or equal to 0, it is 0 position. It is 0 position. And 1 for t greater than or equal to 0. So this is your t greater than or equal to 0 position. So it is a step response. So another unit step function, but it is delaying with respect to a constant a. It is delaying with respect to a constant a. So the u of t minus a you are taken as a function. So it is 0 when t minus a is less than 0 condition or t is less than a condition, and it must be 1. So t minus a is greater than 0 condition or t must be greater than a condition. So similarly, another what you can say acceleratory constant of t is equal to a minus a. So it is also unit step. So you referred for unit only. So t plus a. So here 0 is t plus a less than 0 or t is less than minus a condition. So this is the function. And 1 for t plus a greater than 0 condition, or you can write it as t is greater than minus a condition. So this is a unit step response. So without delay is the first equation, with delay and with acceleratory delay. So these are the three periodic functions you are representing. So similarly, delta function means it is a impulse. So the definition of an impulse is at t is equal to 0, it must be infinity. It must be infinity. Then you can say that it is a impulse function. So if it is a unit impulse at t is equal to 0, it must be 1. It must be 1. So from 0 minus to 0 plus delta of t dt is equal to 1. Then you can say that it is a unit impulse function. Okay. So general functions can be defined as delta of t is equal to du of t by dt. So 0, t less than 0, undefined, t is equal to 0, 0, t greater than 0. So that means it must be always in the y-axis only. It must be always in the y-axis only. So this is a delay timing conditions of the delta functions. So particular functions, so there must be two different time values will be there. So if you take this as t1 and this as t2, so we can get one equation. So this as t1 and this as t2, you can get one equation. Or this is t1 and this is t2, you can get one more equation. Like that you can represent a function in a equation form with respect to range of values of t's. Range of values of t's. So similarly, the last test function is ramp signal. So here also I have taken a unit ramp. So ramp means it is passing a straight line through origin. So how you can write y is equal to mx. So y is equal to mx means dy by dx is the m value and x. So that is y value. So here y is r of t. Y is r of t. So dy by dx is unit slope and x is t axis. So t axis in this in the time axis only. So r of t is equal to 1 into t, or r of t is equal to t. Okay. So for unit step response, the equation can be represented as like this: r of t is equal to minus infinity to t minus infinity to t. So u of tau d tau is equal to t into u of t. So if unit value is there, u of t is equal to 1. So if 2 units are there, u of t is equal to 2. Like that you have to represent. So finally the r of t value must be 0, t less than or equal to 0 condition, and t greater than or equal to 0 condition. So similarly the ramp function having certain delay. So certain delay. So r of t minus t of 0. So t of 0 is the delay. So at that time, so 0 means t2 less than or equal to t naught, and t minus t of 0. So it is t greater than or equal to t naught. So this function we are getting after t greater than or equal to t naught only. So before that it must be 0. Before that it must be 0. So similarly advanced t. So you can go for the ramp function. So that is r of t0 is equal to, so 0 means t less than or equal to minus t naught, and similarly t plus t naught is t greater than or equal to minus t naught. So minus t naught onwards you are getting a ramp function. Before that it must be 0 only. So are you understand? These are the different test signals involved in the transient responses. There are exponential is there, parabolic is there, any different periodic functions you can use. There is no problem. So with respect to that, you have to write a equation, then you have to substitute in the original basic equation, then you have to go for the time domain analysis, or you can go for the Laplace transform analysis. So now there are comparison with time domain and Laplace. So u of t unit. So unit time can be represented as 1 by s. So e power minus at can be represented as 1 by s plus a. So sin omega t can be represented as omega divided by s square plus omega square. So cos omega t can be represented as s divided by s square plus omega square. So df by dt can be represented as s into f of s minus f of 0 plus. So integral 0 to infinity f of t dt can be represented as f of s by s. Then f of t minus t. So that you can write it as e power minus t s f of s. So similarly some constant is there. So it is a dc. So e by s. So similarly e power at. So 1 by s minus a. So sin omega t plus theta. So s into sin theta plus omega into cos theta divided by s square plus omega square. Cos omega t plus theta. So s into cos theta minus omega into sin theta divided by s square plus omega square. So d square f of t by dt square. So here s square f of s minus s into f of plus minus f of plus. So similarly e power at f of t. So f of s plus a. So t can be represented as 1 by s square. So if t square is there, 1 by s power 3. So t power 3 is there, 1 by s power 4. So 1 represents 1 by s. So t is multiplied by 1 by s square. T square is multiplied by 1 by s power 3. Like that you have to go for the time domain to Laplace transform. So here I have taken a simple example for calculation of the constants, how you are going for the residues. So they are given a function. So f of s is equal to s square plus ps plus q divided by s plus a plus s plus b plus s plus c. So this, the partial differential equation can be represented as the residue k1 divided by s plus a plus the residue k2 divided by s plus b plus the residue k3 divided by s plus c. For finding the residues k1, k2, k3, so just the overall function is multiplied by denominator of the each residue. So that is s plus a into f of s, and substitute s is equal to minus a. So similarly for k2, so s plus b into f of s, and substitute s is equal to minus b. So similarly for k3, s plus c into f of s, and substitute s is equal to minus c. You can get the values of k's, k1, k2, k3. So once you are getting those values, you have to substitute. After that, you have to go for the calculation of inverse Laplace transform. You can get in terms of time domain equations. You can get in terms of time domain equations. So similarly, another example. So f of s is equal to a divided by s into s plus b. So that I am writing as k1 by s plus k2 by s plus b, where k1 and k2 are the residues. So if you substitute for k1, s into f of s, such that s is equal to 0, and k2 s plus b into f of s, and substitute s is equal to minus b. So you can get a by b into 1 by s, a by b into 1 by s plus b. So finally you can get a by b into 1 by s minus 1 by s plus b. So here also if you multiply, you can get the original equation only. Okay. So coming to the conditions of the passive elements with and without initial conditions with the time domain and Laplace transform. So in time domain, the resistor V of t is equal to R into I of t, voltage drop across the resistor. So while you are writing in terms of S domain, so V of s is equal to R into I of s. So for an inductor, V of t is equal to L di by dt. So in S domain, so you have to write V of s is equal to S into L into I of s. So similarly, if there is any initial current is there, so the equation V of t is equal to L into di of t by dt minus I of 0. So in Laplace transform, so V of s is equal to S into L I of s minus L I of 0. So similarly for inductor current, so I of t is equal to 1 by L integral V of t dt. So in terms of Laplace, so I of s is equal to V of s divided by S into L. So for a inductor with initial condition, the current I of t is equal to 1 by L integral of V of t dt minus I of 0. This can be represented as I of s is equal to V of s divided by S into L plus I of 0 by S. So coming to the capacitor current, So I of t is equal to c dv t by dt. So I of s is equal to s into c into v of s. So without initial conditions. So with initial conditions, I of t is equal to c into d v of t by dt minus v of 0. So the Laplace transform current I of s is equal to s into c into v of s minus c v of 0. So similarly, without initial condition, the voltage drop across the capacitor is 1 by c integral I of t dt. So in the Laplace transform, V of s is equal to I of s divided by s into c. So if it is a initial conditions are there, so then V of t is equal to 1 by c integral I of t dt minus v of 0. Then Laplace transform V of s is equal to I of s by s into c plus v of 0 by s. So this is the comparison of the time domain and Laplace transform with and without initial conditions. So here also see the resistor, you don't have any changes with and without initial conditions. It remains unchangeable. It remains unchangeable, but inductor and capacitor must be changes accordingly. Okay. Then coming to the initial value theorem and final value theorem for Laplace transforms. So to understand this, if f of t and its first derivative are Laplace transformable, then the initial value of f of t is you are finding. So that is f of 0 plus is equal to limit t turns to 0 f of t, limit s turns to infinity s into f of s. Okay, so to understand this, I am going for the first derivative of f of t. So integral 0 to infinity df of t by dt e power minus st dt is equal to s into f of s minus f of 0 plus. So we are taken in terms of the Laplace transform. So to go for s is equal to infinity, so I am multiplying both sides by limit s turns to infinity. So limit s turns to infinity. So df of t by dt e power minus st dt is equal to limit s turns to infinity s into f of s minus f of 0 plus. So here s turns to infinity. So e power minus infinity you can get. So that means LHS is 0. RHS is limit s turns to infinity s of f of s minus f of 0 plus. So from that what you can get, limit s turns to infinity s of f of s is equal to f of 0 plus, your initial value only. F of 0 plus means it is the initial value of your function only. Okay. Then coming to the final value theorem. So if f of t and its first derivative are Laplace transformable, then the final value of f of t can be represented as, so final value t is equal to infinity condition, limit t turns to infinity, f of t is equal to limit s turns to 0 s of f of s. So to understand this equation, so I am going for the Laplace transform of your first derivative of f of t. So limit t turns to 0, df of t by dt e power minus st dt is equal to s into f of s minus f of 0 plus. Now the s is reaches 0. The s is reaches 0. So limit s turns to 0. So integral 0 to infinity df of t by dt e power minus st dt is equal to, so RHS also you have to multiply by limit s turns to 0 s of f of s minus f of 0 plus. Then this value, so integral 0 to infinity df of t by dt into dt, so that t turns to infinity condition df of t by dt into dt is equal to limit t turns to infinity f of t minus f of 0. So by substituting these two equations, or comparing these two equations, you can get at t turns to infinity for a limit of f of t, the limit s turns to 0, s of f of s. So finally you can get the same thing only. So this is your final value theorem. So then coming to your conventional integral, conventional convolution integral. So here the convolution integral is multiplication of the two values under integration, two values under integration. Okay, so let us take some impulse response with a time shift. So f of tau of t is equal to uh, h of tau of t is equal to h of t minus tau. So a delay angle is there. So now the linear time invariant system y of t is equal to, the output of the system y of t is equal to minus infinity to infinity of a integral. So x of tau h of t minus tau d tau. Then this expression, after going for the mathematical derivation using the superpositioning integral or convolution integral, so finally you can get it as, so the output y of t is equal to the input x of t into h of t, into h of t. So to understand this, we are going for a simple problem. So h of t is equal to e power minus t and f of t is equal to e power minus 2t. So I am going for the multiplication of the two equations. So taking inverse Laplace of capital H of s into f of s. So e power minus t you can write it as 1 by s plus t, s plus 1, and e power minus 2t can be represented as 1 by s plus 2. So Laplace inverse of 1 by s plus 1 into 1 by s plus 2. So Laplace inverse of taking the LCM and residues. So 1 by s plus 1 plus minus 1 by s plus 2. So finally you can get e power minus t minus e power minus 2t. So here this is a exponential function with subtractive element, but the input is multiplication of the two values, multiplication of the two values. So that is the advantage of convolution integral. Okay, then coming to the main topic. So the first case, RC circuit I am taking, a DC voltage I am taking as a step response. So the maximum value of voltage is V volts. So at t is equal to 0, the maximum value is V and it is constant forever. Then you can call it as a step response. So if a particular time it reaches to 0, then it will become as a square response. Square response. So almost the step response and square response will give the same equation solutions only. So now for a RC circuit, there is no initial charge or voltage across the capacitor. So let us assume the capacitor is under relaxed position. Okay. So now a switch K will be closed at t is equal to 0. So once the switch is closed, there is a closed path. A current of I amperes will flow through the RC circuit. So the switch will be closed at t is equal to 0 means you can get two conditions. One is t is equal to 0 minus condition and another one is t is equal to 0 plus condition. So now what is the voltage drop across the capacitor when t is equal to 0 minus condition? So what is t is equal to 0 minus condition? Immediately the switch is closed position, which means still the switch is open only. Still the switch is open only. So no current will flow through the circuit. There is no voltage drop across the capacitor. So you are already assumed that the capacitor is under relaxed position. So V of 0 minus is 0. Then the switch is closed at t is equal to 0 plus, just immediately the switch is closed position. So under that condition, the current will flow through the circuit. The supply voltage is connected across the RC circuit. So capacitor never takes the instantaneous voltages. The capacitor acts like a short circuit. The capacitor acts like a short circuit. Then what is the voltage drop across the capacitor? So Vc of 0 plus is also 0. Vc of 0 plus is also 0. So under that condition, the initial current I of 0 plus is only the resistance and voltage are connected in series. So V divided by R you can get at t is equal to 0 plus condition. Are you understanding? Then I am going for the writing of KVL equation. So here a voltage source is there, resistive drop is there, capacitive drop is there. So by applying the KVL, so R into I is the voltage drop across the capacitor plus 1 by C integral IDT is the voltage drop across the previously voltage drop across the resistor. Now 1 by C integral IDT is the voltage drop across the capacitor is equal to V. So here integration is there. So you cannot directly go for the calculation. So you have to go for differentiating the first equation with respect to t. So R into di of t by dt plus 1 by c integration and differentiation gets cancelled. You can get I is equal to, so the given is a step response. Step means it is a constant. Constant differentiation is 0. So this is the equation you are getting. So then di of t by dt is equal to 1 by RC into I, that is equal to 0, or you can write it as capital D plus 1 by RC into I is equal to 0. So it is a first order homogeneous differential equation. It is a first order homogeneous differential equation. The solution for this first order differential equation carries with only complementary function. So that is what I of t is equal to some constant a e power minus t by RC. For finding the constant a, you have to substitute the initial conditions. So already you derived the initial condition I of 0 plus is how much? V by R. I of 0 plus is how much? V by R. So now the equation 3, by substituting t is equal to 0 plus condition, so I of 0 such that t is equal to 0 plus, so a e power minus 0, so e power 0 is 1, so you can get only a value. So what is that value? It is V by R only, V by R. Okay, so therefore the value of I of t is V by R e power minus t by RC. So R you can write it as I of t is equal to V by R e power minus t by tau, where tau is a time constant. So tau is R times of C. Tau is R times of C. Are you understanding? So this is representation of a term tau. So it is a time constant. So this time constant is multiplication of R into C. So once you calculated the current flowing through the circuit, then the voltage drop across the capacitor. So what is the equation? 1 by C integral IDT. Then substitute I value is V by R e power minus t by tau. So if you substitute 1 by C integral 0 to t V by R e power minus t by tau dt. Then go for the integration. So V by RC 1 by minus 1 by tau e power minus t by tau with the limits of 0 to t. Okay. So then V by RC minus RC e power minus t by tau with the limits of 0 to t. So here the numerator and denominator RC is there. So finally minus V e power minus t by tau minus 1. So the minus if you multiply, so V into 1 minus e power minus t by tau. So this is the voltage drop across the capacitor. voltage drop across the capacitor. Are you understanding? So now coming to the response of the voltage drop across the capacitor and current flowing through the capacitor. So what is your current flowing through the capacitor? So V by R e power minus t by tau. And what is your voltage drop across the capacitor? V into 1 minus e power minus t by tau. Okay. So if t is equal to 0, if t is equal to 0, so this value is 0. So e power 0, so e power 0 means 1. So e power 0 means 1. So the final value you can get it as V by R. So that's why the current waveform starts with V by R. So similarly, so here if you substitute for the voltage drop across the capacitor with t is equal to 0, so V into 1 minus e power 0. So V into 1 minus 1. So finally 1 minus 1 is 0. So voltage drop across the capacitor is 0. So this is the point where the t value is equal to 0. Okay. So now if you gradually increase the time value, the current will be decreases because exponentially decreasing order. So the capacitance value, voltage drop across the capacitance value will be exponentially increasing order. Are you understanding? So now what is a time constant? What is a time constant for a RC circuit? Are you understanding? So the time constant can be defined as, the time constant can be defined as, it is the time required for the transient response to attain 63.2% of the steady state value starting from 0. Starting from 0. So please remember, so the time required for the transient response to attain 63.2% of the steady state value starting from 0. So that means so this is your VC value starting from 0. This is your VC value. So once it reaches 63.2%, so how it will reaches 63.2% means, so the voltage drop across the capacitor is V into 1 minus e power minus t by tau. So if you substitute the t by tau value is equal to 1, so that you can call it as one time constant, that you can call it as one time constant. So the voltage drop across the capacitor is V into 1 minus e power minus 1. So finally you can get the value as 0.632 into V, where V is the applied voltage, where V is the applied voltage. Okay, so for that, at a value of 63.2%, so this is your time constant, the time taken to required from starting 0 to this value is your time constant value tau. So this value is how much? R into C for a RC circuit. For a RC circuit. Are you understand? So similarly, if you want to go for Laplace transform for the same circuit, initially the capacitor has no charge, so voltage drop across the capacitor is 0. At t is equal to 0, the switch will be closed. So a step response V volts is applied and a resistor is connected in series with the capacitor, and a switch K at t is equal to 0, it will be closed. So a current of I of t will flow to the circuit. So the conditions are same. So I of 0 minus voltage drop across the capacitor is 0 because no current will flow through the circuit. At t is equal to 0 plus, immediately the switch is closed position. Voltage drop across the capacitor is 0 because capacitor never takes the instantaneous voltages. So under that condition, only the resistor and voltage are connected in series. So the capacitor will be short circuited. So under that, the initial current I of 0 plus is V by R. Okay. So then coming to the basic equation, voltage drop across the resistor R into I, voltage drop across the capacitor 1 by C integral I dt is equal to V. So now taking Laplace transform of equation 1, R into I of S plus 1 by C into S I of S is equal to V of S by S. So remember, it is a step response. It is a step response. For step response, you have to go for V of S by S. So then R into I of S plus 1 by C S into I of S is equal to V of S. Now I am taking I of S as common. So R plus 1 by CS is equal to V of S by S. So I of S is into RCS plus 1 by CS is equal to V of S by S. So I am taking RC as common. I of S into RC into S plus 1 by RC divided by CS is equal to V of S by S. So I of S is equal to V of S by S into, so C of S by S plus 1 by RC into 1 by RC. So here the C value gets cancelled, S value gets cancelled. So you can get V of S by R divided by S plus 1 by RC. So if you take inverse Laplace transform, so I of S inverse Laplace transform is I of t. So V of S inverse Laplace transform is V of t. So V by R 1 by S plus 1 by RC is e power minus t by RC. Or you can write it as E of t is equal to V by R e power minus t by tau, where tau is R into C. It is a time constant for RC circuit. So are you understand, students, all of you, how you are going for the time domain analysis and the Laplace transform analysis? So here the most important thing, the steps wise also you can identify that in a time domain analysis, so you required the more calculation. So complementary function or particular integral, then you have to substitute the initial values, then you have to get the solution. But while you are going for the Laplace transform, very few steps you can get the solution. Are you understanding?